So hello, good morning, everyone. My name is Saad Akhtar, as Charles mentioned, and I was a former postdoctoral fellow at the Department of Mathematics and Industrial Engineering at GERAD, and I was supervised by Professor Charles Saad and Professor Bruno Blay from the Chemical Engineering Department. Now I'm a staff researcher at the National Renewable Energy Lab now, and I work as a thermal modeler in the Advanced Vehicle Charging Infrastructure group here, where we do a lot of work in decarbonizing like commercial fleets, and also like advanced powertrain modeling applications, and so on and so forth. So today, the topic of my presentation or webinar is basically an overview of most of my postdoctoral work at GERAD. And I worked on optimizing the overhang control using density gradient-based method, and we applied it to both thermal and thermo-fluid application. This project it was basically a part of a bigger consortium of Metal Tech, which is like an industry collaborators to improve industrial efficiency of cooling channels in different industrial applications. Most of them geared towards like aluminum manufacturing industries, like to manufacture aluminum parts using molds and dies. So our key collaborators for this project was National Research Council Canada, specifically Marc-Etienne Lamarche-Gagnon, who's a research officer there. He's our close contact for this project. So let's move to the agenda. So I'm going to start with a quick motivation and background of this work that we undertook, basically starting with the overall physical problem first, and then I'm going to start giving a brief overview of the additive manufacturing constraints. What were those basically, and how did we, like, what approaches were there in the literature, a brief overview of that, and basically what approach did we select and why, and what are some of the results that we got after we incorporated that approach within the bigger topology optimization approach. So that leads to, the background would lead to the research question that was formulated. And then I'm gonna start, that is gonna proceed with the bigger overview of the topology optimization with an example that was done in the first part of my postdoctoral work. And also I'm gonna, following that, I'm gonna outline mathematically different approaches for additive manufacturing constraints that we seriously considered and implemented and tested. And then after that, the one that we selected and the one that we formulated, some of the key outcomes from that after we integrated that approach within the topology optimization framework that was built at the National Research Council. So without further ado, let's move on. So a bit of a motivation regarding the project. So a bit of a background for those of you who are not familiar with conformal versus non-conformal cooling channels. So cooling channels are sort of an important part in manufacturing aluminum components, especially using molds and dies. And how so? You want a very accurate control over the thermal management of these parts. So traditionally what has been done is, as you can see on the left side of this figure, the traditional cooling channels are more using like straight drills in the mold. So if you look at these channels, they're like straight pipes that are joined together, and they're built mostly using engineering judgment. But the problem with these is, like, if you look at, like, the bends are pretty not so sharp, pretty sharp, sorry, and also they don't really surround the part in an optimal way. So basically, as opposed to if you look at the picture on the right, where the cooling channels are basically surrounding the whole part in a very shape conforming way, if I may. So the goal, I mean, the difference between the first approach and the second approach is basically it has a lot of ramifications in the cooling time, overall cooling time. So if the cooling is non-optimal, then that results in a higher and non-uniform cooling, higher cooling time and non-uniform cooling, which can result in bad part quality. So from that, the important design parameters and constraints to consider are basically the design and proximity of the cooling channels, like I mentioned earlier, and what type of material you use for the cooling channel, and also like you can design all you want, but at the end of the day, what matters is what you can manufacture, right? Using the existing manufacturing technologies. With the straight channels, the good thing is like the manufacturing technologies are pretty robust. You don't really need that complicated part manufacturing technologies, but with conformal cooling channels, you need to make sure that whatever you're designing, you can manufacture. And that was like a big part of this project. Our collaborators were really interested in knowing whether the additive manufacturing techniques such as laser powdered bed metal fusion, which basically can manufacture complex parts using metal powders, whether it can be used to manufacture such conformal cooling channels. And yeah, that was the main outline of the overall project, that we wanted to know whether, okay, like can we manufacture these cooling channels using additive manufacturing? What are going to be the roadblocks? Can we sort of build an integrated framework which can give us optimum topologies which can be manufactured? And I'm gonna, in the next slide, like here now, I'm gonna highlight what I mean by like what are some of the roadblocks or some of the problems that you can face when you go the additive manufacturing route. What do you need to consider to build a part? So topology optimization, like I just mentioned, it's sort of optimization of material placement, or optimization of building the efficient cooling channels if you give it a certain cost function, if you give the optimizer a certain cost function. And it does allow you to come up with these ingenious ways of building complex geometries that are easier and potentially cheaper to manufacture through additive manufacturing. However, like I said, they are limited by certain constraints, and one of the major constraints is build angle. And this picture on the right, it demonstrates it very aptly. So consider the figure A, where you have the overhang without support material. And by overhang, I mean that the part is curved so that the gravity is acting on it as you move up the layer. So just to give those of you who don't have a background in additive manufacturing, so additive manufacturing is a layer by layer process. You start at the bottom of the build plate. Build plate is it's a platform where you build your part on top of, and in the direction normal to the build plate, which is referred to as build direction here, the part is manufactured layer by layer. So if your part has certain features which require it curving at certain angles, then that could sometimes be a problem depending on how severe is the curve. So for example, in the figure A here, the angle is 65 degrees with the build plate. So it's gradual enough so that the modern additive manufacturing technologies can withhold this amount of curve. But if you want to go beyond, let's suppose below 45 degrees, like if you look at part on your right, which is right at the threshold, if your part has certain features that are more pronounced than 45, then you may find some sort of, like, gravity might act on this part and it may warp it in certain way, and it may reduce the quality. It can distort, it can cause some distortions. There's some thermostatic stresses too that can act at this angle, and that can also cause some distortions within the part. So almost always, like most of the traditional approaches to prevent that is like you use some sort of support material in that, and you need to support those overhanging regions, and then you remove that support material that are not really a feature of the part that you're trying to manufacture later on through post-processing or melting. But for the technology that we were considering as laser powdered bed fusion, we were tasked the support material for our case was not really ideal because it significantly increases the post-processing cost of the material, and it's also harder to do that for LPBF. So our question, or the bigger question that we were asking ourselves at the beginning of the project, were can we build self-supporting structures within the topology optimization framework? Can we build a framework which optimizes the topology while also considering the manufacturability constraint? So using this as a motivation, so that was our bigger research question, that how can we develop a digital design platform for topology optimization of cooling channels using laser powdered bed fusion. And there are two core parts that I want you to think of. The first one is topology optimization, which I'm going to talk about in a bit more detail in the next section. And then adapted to additive manufacturing. That's another big part. Topology optimization itself, there's been a lot of work that has been done, especially in the structural part. Not so much in thermal and thermo-fluid. There are some studies in thermal, but thermo-fluids, it even gets more complicated because of the high degree of freedoms that you have to deal with in the problem. So yeah, topology optimization basically translates to identifying the ideal placement of cooling channels for uniform cooling within the mold. And then the additive manufacturing adaptation is we want to ensure that the designs that we built using the topology optimization, they can be manufactured. Specifically, they can incorporate this additive manufacturing constraint. So before I jump on to the additive manufacturing, so I'm moving on to the section where I explain a bit of like how the topology optimization works, specifically in context of thermal problems. So yeah, let's talk about that. So let me give you a problem which I was trying to solve like at the beginning of my postdoc, just to get a hang of how the topology optimization works and what are some of the parameters that it is dependent on. So consider a metal plate, or just like or a plate. And the plate can be composed of two materials. One is insulator and other is conductor. And you're given a specific volume fraction of a conductor. Let's say 15% of the plate should be manufactured using a conductor. And that is your constraint. That is your constraint on the material. And the plate has uniform heat generation with a heat sink on the side, on just one left-hand side, as shown in this figure. So, sorry. The question is, the topology optimization question is, how can I optimize the placement of my conductor material so I get the least average temperature in the domain, so that I can reduce the average temperature in the domain. So for this particular case, our cost function would be the average temperature in the domain. So, okay, let me just move this banner. Side. I'm sorry about that. Yeah. So yeah, first, of course, you start with so here you want to solve it for the temperature field, and you want to optimize the placement of these the conductor material such that you get a minimum temperature. So of course you have to solve the heat conduction equation for temperature. Temperature is your is your thermal parameter here, but your design variable here is the placement of the material. It's the density, which we call density in topology optimization language. So you want to optimize the density, and the density depends on the discretization of the domain. So if you want a finer accuracy in your finite element problem, you have to discretize it fairly well. And so each discretized element is a variable of your topology optimization problem. And for complicated problems, you can imagine that could result in like hundreds of thousands and even millions in some cases of design variables. You got to figure out a way of formulating your optimization problem and choosing an optimization framework that can accurately solve that. So this basically shows the flow chart. So we use so here in this code, I used Galerkin method of weighted residuals for solving the finite element problem. And then for sensitivity analysis, so we implemented both adjoint method and finite difference method just to see the advantage of adjoint method over the finite difference method for sensitivity analysis. And of course, there are some filters that you need to apply in topology optimization. Topology optimization is notorious for having these like checkered related problems as you go finer in the grid. So you have to implement a certain regularization approach to limit the minimum size of the feature that you want. So that's what the design variable and gradient filtering does. Actually, not that's what the regularization filter does. The design variable and gradient filtering actually it ensures that the optimized topology designs that you get are more black and white, so you can have a more sharp solution rather than the diffuse solution. So the whole flow goes like this: you initialize your solution, you do a finite element analysis, and then you calculate the sensitivities of the variable with respect to densities. And then, of course, you filter the densities to eliminate the checkerboard problem. And you feed that into the optimization framework for this particular problem. We sampled the method of moving asymptotes because that is the convention in the topology optimization community. It's very popular. It's easy to compute, and you have the gradient, so you can. So there is a very. I'm going to talk about the gradient in a bit, but there is a very interesting way of formulating your adjoint problem such that it becomes self-adjoint. So let's get more into it. So here's the overall adjoint problem for the setup that I just showed you. So your cost function is basically average temperature or heat flux in the domain, and you want to minimize that. And the constraints on your optimization problem, you have the volumetric constraint of the conductor material, like I said. It can be 15%, can be 20% material, whatever you want. And then you have the upper and lower bounds on the design variable. So design variable is between 0 and 1. 1 means, okay, place the conductor material at that particular point in the domain, and 0 means that it's an place the insulator material. So in an ideal world, you would get like, a binary 0-1 solution, but with that makes the problem really stiff. So basically what we do is we make it a bit of a continuous problem so that we can compute gradients, and then we use the regularization approach, not really the filtering approach, basically, to get like the black and white designs. And we use the adjoint method to calculate the sensitivity of the cost function with respect to the design variable, which is the density of the material in this case. I mean, by density, I mean the placement of conductor material versus insulator material. So this distinction is very important in this case. So whenever I talk about density, it's not the conventional density, it's the material placement density. Anyway, so we rewrite our cost function in this way, and we use the equilibrium equation, which is a conduction equation in our case, and we define an arbitrary fixed real vector u tilde t. And rewriting your cost function in a smart way. So this 0 here can be replaced by this equilibrium equation here. And if you want to calculate the sensitivity with respect to the design variable, you differentiate this. And at the end of the day, using this adjoint equation, you simplify your sensitivity to this expression, and this basically implies that it's in the form of our equilibrium constraint. It implies that the new variable that you assumed, it's actually the original variable of the problem. So U here refers to the temperature of the domain, and this self-adjoint problem has consequences in terms of computational time, because it saves a lot of time since the cost of computing the gradients. It just reduces to basically the cost for solving the FEM problem just once. And to demonstrate the effectiveness of this problem, I'm going to show you in the next slide. Let's see, it's here. Yeah. So we also calculated the sensitivities using what should I say, finite differencing, which is a very crude way of measuring sensitivities, but it requires like constant iteration of the FEM problem for each iteration of for each grid point, and that could, like, basically, if you scale up your grid, that could be very cost kind of penalizing. Like, you could penalize your cost a lot. So just to demonstrate, how the topology. So we built this program. We built this. We just implemented it in Python just to test it and compare the two different approaches. It was more for my own edification than anything else, but the results were staggering. So if you implement the topology optimization using the adjoint problem, you would get the optimized conductor material distribution. The conductor material here is in the red, by the way. So if you look at these designs, they should remind you of something very common in nature. So it's more of like a fractal design. And that's how, like, if you look at in nature, like the tributaries, that's how they maximize their flow. The rivers, and also, like, in the leaf, the transport of important micro and macronutrients for plants. They're also, like, the leaf structure is also based on this. But anyways, that was a bit of a tangent. But coming back to the problem here, especially with regards to the computational time, the adjoint problem solves this thing within a few seconds, whereas the FDM approach for this particular grid, which is 60 by 60, and now there's like the discretization in the X direction and discretization in Y direction. So it's like 3,600 design variables. And filter here is the filter of the minimum, which is the minimum length that you want in the, so that it just filters out features that are not really realistic. So you give it a filter radius and use the optimizer, and at the end of the day, the FDM approach, it takes about 50 minutes. So that's like huge cost when you compare these two. So that's so that was the motivation of basically the point is, so we went on from here, went on with the adjoint problem for all of our topology optimization frameworks, and they are like, if you formulate your problem in a smart way, you can make the problem self-adjoint, and that has very interesting, important, should I say, corollaries in your overall problem. Because the computational time specifically in this case matters a lot, because if we want to scale this up to thermofluid and problems, thermofluid is even more complicated. You're solving more equations. It's not just temperature. You're solving for flow, solving for Navier-Stokes. That can get increasingly complicated. So you want your sensitivity calculations to be as efficient as possible. So yeah, that's the whole motivation of adjoint. So now this concludes like one of the sections of my presentation, which was a brief overview of the topology optimization approach. I can of course go on into detail, but that wasn't like the real focus of my research. And so now let's move on to the next part, which is the overhang angle constraints, or the additive manufacturing constraint that I talked about in the beginning when I was talking about the build angle and so on and so forth. So our goal was basically, our collaborators at National Research Council, they already built a very robust topology optimization framework in-house, and they were looking to figure out ways to incorporate the additive manufacturing constraint, because their topology optimization framework did not incorporate that at the time. And so that was our main, that was the crux of the project. And so basically, just to give you a brief overview of the overhang and constraint, the literature is still burgeoning in this field. You see a few papers start popping up in this field 2014, 2015, with the interest ramping up recently, but even then it's not nearly as saturated. There are a lot of open questions in the area, and most of this literature, by the way, pertains to structural problems than thermal problems, or thermofluid problems, even worse. Like, we didn't even find a single paper that tackled the overhang angle constraint implementation within the thermofluid problem, and we just find one or two papers that incorporated in thermal problems. So there's a lot of room to explore incorporating these constraints within the thermal and thermal fluid problems. So that's, we conducted a very sort of a thorough literature review of different overhang methods, different modeling methods whereby you could consider the overhang within the topology optimization approach. And these are sort of the 7 categories that most of the research lied within. So I'm not going to go into the detail of every one of it, but we're just going to talk very briefly about. So let's start anti-clockwise from the virtual skeleton method. So the virtual skeleton method, it basically uses the truss optimization approach as a first step, and it's sort of it's not like explicit incorporation of the overhang constraints, but rather it reduces and in some cases it also eliminates the support material. So it doesn't 100% reduces the use of support material. And most of the cases, by the way, they had this constraint that you have to have support material for some of these approaches to work, such as virtual skeleton method, and then also like explicit geometric consideration where you can use shape optimization approach instead of the material density optimization approach. That reduces your design variables, but then at the end of the day, the results that you get, they weren't very robust. Level set method is another interesting techniques that you can also incorporate overhang constraint, but that method is more suited for sharp topology optimization approaches, whereas the approach that we had at NRC, it was more of diffuse. Although they are working on building a sharp topology optimization approach or building a more robust, framework for that. And once we have that, like I think level set method would be a good contender to incorporate in the additive manufacturing constraints within those. But that for our problem, it wasn't really suitable. Then there are other temperatures, virtual temperature method, front propagation. Front propagation method, it was very ingenious, but it was computational friendly to track the interface in the AM process. However, it had some problems with regards to explicit overhang incorporation within the topology optimization framework. And so now I'm going to talk about the 2 that stood out to us, and then we really felt that we should test them further. The first one is layer-wise additive manufacturing filtering approach. So that was very natural, since it leverages the natural process of additive manufacturing. Additive manufacturing, like I said, it's a layer-by-layer process, and in this process, it's sort of just like any other filter in the topology optimization approach, like a regularization filter or a filter that give you crisp designs. You could just put this as an extra step in the optimization process, and it filters for the densities that can be printed using additive manufacturing. So this concept was very interesting, and it has some logistic benefits. And then the other method is projection-based method that was that also caught our eye, and most of the overhang modeling categories, most of the research is based uses this method, and to good use, because it's very robust. It allows you. I'm going to talk in a bit more detail in the next slide of the mathematical implementation of these 2 in particular, and and how we implemented this, and which one did we end up implementing in our code as well. So like I said, the 2 approaches that were a good candidate, layer by layer and heaviside projection-based method. And these approaches were chosen because they were computationally viable for the stuff that we were trying to do. And they were also their ease of implementation within the topology. So we didn't had to change our topology optimization framework drastically to incorporate that, which wouldn't be the case for some of the other approaches that we reviewed. So for example, for virtual skeleton method, we would have to make some changes in how we got like topology optimization. Same with the level set method, we would have to change the topology optimization framework from diffuse to a more sharper approach, which at that point we weren't really looking at. So that's why these 2 approaches stuck to us. And let's talk a bit more about these approaches. So first, let me talk about the layer by layer additive manufacturing filter. This approach, like when we looked at it, it looked really promising to us. And I'm going to tell you why. Like it's very easy to understand. It's very intuitive, and it's basically based on the idea of instantiating material that is sufficiently supported below. So, for example, let's consider this dark square IJ of the material, and you want to know the density of the material. So you want to know whether you want to place conductor material here or not. So based on, like, of course, the topology optimization algorithm, the topology optimization results, let's say the topology optimization tells you that, yes, if you place your material here, that's the optimum solution for it. However, you want to look whether it's manufacturable or not, right? So you look at the 3 blocks in 2D below it and 5 or 9 blocks in 3D below it, and you see whether that box has material support or not. And based on this, you select the density of the material. So it's basically differential. There is physical densities that you get from the topology optimization problem, and then you filter them using this additive manufacturing filter, and that filters to as printed densities. And this happens at every iteration within the optimization approach. And it also extends to 3D problems. Of course, like I said, they're practical. It considers the build direction. So build direction, like I mentioned earlier, it's the direction in which your part is built, perpendicular to and build direction is almost always perpendicular to the base plate, although some exceptions are there. But yeah, these are some of the pros. And the cons were that it's hard to generalize for unstructured grids, and it doesn't take into account the overhang angle explicitly. So I'm going to talk about that. So for example, like I said, below 45, you have problems. But here, how do you know that the overhang angle is 45? There's no explicit programming of that into the topology into this filter. It's based on like the number of materials. So that's how you tune your overhang angle. So for example, in 2D case, I said, okay, 3, if the material is supported by at least 3 blocks underneath it, then put it. So the authors say, okay, that sort of roughly corresponds to 45 degrees. If you want more, you can have more material underneath, like 4 or 5, so on and so forth. So mathematically, the AM fabrication model, this filter, it's expressed as like a minimum and maximum operators for the densities, and you can, like, to make them continuously differentiable, and to get the sensitivities for this, you need to make these operators a bit more smoother. So we chose some like smooth differentiable operators for both the minimum and maximum function here. So here, this eta is the printable density. That's what we want, and x is the original density, which we also call blueprint density, and this chi, capital Chi, is the it's the density after. So capital Chi is defined in the equation below. So it's the maximum density of the 3 of the materials below, basically. So this operator basically, like what I said about the support, it ensures that the material is supported. And of course, you need to calculate, your cost function is to minimize the temperature, and you need to calculate your cost function with regards to the density. And now, like the original density, of course, using chain rule, you convert it to the blueprint density, and this part is computed using the adjoint sensitivity analysis. Good thing is it can be easily integrated in the topology optimization code. You get a nice expression for this adjoint sensitivity formulation, and it also can be combined with other filtering techniques. Like the I'm going to talk about cons in a bit, but let's show some. So we implemented this filter within our topology optimization code, like just like to test, and it had a few promising results. So this is again the heat conduction problem. On the right, you have without any additive manufacturing filters. So you see a lot of these features. You have a lower cost function. So you have like 35,000 of cost function, but you see a lot of these features that can't really be manufactured using additive manufacturing. Like these, there are several overhanging regions here. But on the left, like the 4 results that you see. So they're for different build plate configurations. So this blue line is the build plate, and the direction of the build direction would be perpendicular to that. So let's talk about, for example, the south case. It's because it's easier to understand. So the build direction here would be in the y-axis, so going from down to top. Should probably put an arrow there. But as you can see, like some of the features are straightened out here. So you can really see that the filter, it's doing its job. It's eliminating the features that can be manufactured. However, there are certain issues with it with regards to see there some of the areas the design is not really crisp. It's a bit diffused. And of course, like another thing to note, and that's going to be a recurring theme in the results as well, is that you see that the cost function is like it increases when you incorporate the additive manufacturing filter. So there is a cost to making your solution manufacturable, right? Because if you like, the ideal optimal solution is would be without any filter, and it would be, you know, just what I've shown on the right. So you've seen like 35,000 cost function, and the cost function increases once you add this constraint, which is pretty understandable. So that was on the conduction problem. So we also reproduced some of the results from Langlar's paper, because this filter is mostly, like I said, most of the topology optimization work is for structural, in the structural domain, and to good use. So we tested our code for full different build direction on the minimum compliance problem as well, which like to minimize the stiffness of the problem. And the additive manufacturing filter, it also allowed for these support structures while minimizing the objective function. So that was also one of the like important things in testing this filter, that it works on a wide variety of problems, and it also works on different build directions and different build plate configurations and so on. So that was layer by layer filter. The biggest problem that we found with layer by layer filter was, of course, it's we were interested for 2D problems and for structural problems. Yes, it works, like I demonstrated, but we were more interested in how do we scale this up to more complicated thermo and thermofluid problems, and that's where we figured like it mostly works on structured grids. And another thing was that you cannot really explicitly incorporate the overhang angle if I want to. So let's suppose if my technology can withstand an overhang angle of 65 degrees, I don't really know for sure how can I formulate my layer by layer filter in a way that hits that 65 degree constraint. So that was the reason of us exploring a heavy side projection based method, and which is a much more detailed, a much more robust method of incorporating the minimum overhang angle within the density based topology optimization. The good thing was it's very natural to implement this within the density based topology optimization frameworks. So that was really a big motivation for us. And so basically how it works is it's based on integral of the density, heaviside projected integral of the density gradient, and through constraint you can implement constraints on the overhang angle projection, and you can control the overhang angle projection in that regard. I want to talk about the mathematical formulation in a bit of a detail, but it was very interesting, and once you think about it, it was a very logical way of incorporating accurately the minimum overhang angle constraints within the design formulation. And two of the formulations that are normally discussed within the heaviside projection based method are the projected undercut perimeter based and the projected perimeter based formulation. So we're not going to talk, like undercut control wasn't really a problem for us, so we didn't really explore that much into the detail. We kept our focus on the minimum overhang control, which we were more interested. So that's what I'm going to talk about in the next few slides. The pros, like I said, explicit consideration of the overhang angle. Its implementation was relatively easier into the framework that was already built at the NRC. And the good thing is it can also be easily extended to 3 dimensions and to unstructured grids. So that was a big motivation for us. And cons, I'm going to talk about in a bit more detail, and how we got around that con, which was using additional grayness constraint to penalize the intermediate densities. So let's talk about the mathematical formulation of this problem. So this is the whole compliance. So the compliance here could be like I said, like for thermal problems, it could be average temperature. For thermo-fluid problems, it could be temperature and the pressure losses penalty. And the equilibrium constraint for is your governing equations. So for example, for thermal problem, that would be your conduction equation, heat conduction equation. And the volumetric constraint here is, like I said, the percentage of the conductor volume that you want in your domain. And if you look at the gamma here, refers to the density of the material. So it's, and there are a couple of, so there's gamma tilde and then the gamma tilde bar. So this tilde, and so gamma itself just represents the original density. And gamma tilde is after you filter this density. So like I said, in topology optimization problem, we need those filters. Those filters are important because like you want a minimum length scale control, because otherwise you'll end up with checkerboard pattern. So that's what the tilde refers to. And it's also called density filtering. So for density filtering, we used Helmholtz PDE approach to control the density, to control the minimum length scale. And then you also filtered that filtered density using a heaviside filtering. And the goal for heaviside filtering is to basically alleviate the grayscale transition between the black and white densities in the optimized design. So like I said, we make the problem continuous because we want to calculate the gradients. But then, between 0 and 1, we would need certain, so at the end of the day, after we don't want it continuous. So we want to basically have like a sharp transition between 0 and 1, where 0 means, okay, place an insulator material here, and 1 means place conductor material here. There's a mathematical representation of the heaviside filtering that we use. The important part that I want to, divert your attention towards is this fourth equation, which is the overhang constraint using the projected perimeter. So basically, we implemented the overhang angle constraint as a constraint within the topology optimization instead of filter. So that's the bigger difference with the other approaches. And you constrain the overhang angle by actually constraining the projected perimeter that those overhang angle will project on the base plate. So the expression on the left is basically, if you look at it, it's the heaviside projection on the build plate of the projected angle of the overhang material. And that was a very interesting way, and that was like actually a very intuitive way of incorporating the projected perimeter constraint within the topology optimization and also controlling the overhang channels. So this perimeter, this projected perimeter is a very important parameter, and there are currently no real guidelines in the literature as to how this projected perimeter, like what value should we use of this projected perimeter? Does it scale well with the target volume or with the volumetric constraint of the problem? So these are some of the problems that we had to face. And I want to talk about these problems just in a bit. So just to know how effective this was. So this is the effective projected perimeter for overhang constraints. So you use different values. So this TRG OH is the target OH. It's the value of, it's the P bar alpha bar. So that's the projected perimeter value. So for different projected perimeter values, you see how how the designs change. So as you can see, so for the no, like if you compare these with the no overhang constraint approach, so as you go higher in your projected perimeter constraint, your solution approaches the no overhang constraint. But you can see this approach clearly works as well. So there are a few designs, overhang features that were eliminated by incorporating this. And beta max is basically a perimeter in the heaviside projection. It basically ensures how sharp your transition between 0 and 1 would be. So the higher, the sharper. So So you have to use same beta max value if you want to compare across designs. So again, the same problem with, we implemented that within the 3D heat sink problem, and we got some promising designs as well. But the bigger question here, so here you can also see, like with the overhang constraint, there are several overhang features that you can see, and like after implementing the target OH value, or after implementing the projected perimeter constraint, you get much more manufacturable designs at a penalty of your cost function, of course, but that's something. But now the bigger question is that we've established the target OH is essentially a measure of the projected area, and the lower the better, and the low values of target OH result in stiff optimization problem, and they cause a high spike in the function. So how low a value can we set? And the literature normalizes the target OH value by the representative area of the problem, but is that the best way to do it? Can we normalize it using target volume, or should we normalize it using the projected area of the base case? So these are some of the questions that we're asking ourselves, so that we could get a more robust understanding of how we should set this value for both thermal and thermofluid problems, because we want this methodology to be as agnostic to the problem as possible. We didn't want it to depend on a particular problem. So that's why it's very important for us to develop those guidelines. And those guidelines almost like they don't exist in the literature, and it's just trial and error. So we wanted to basically get a more deeper, in-depth understanding of the process. So doing that, like for the 2D heatsink problem, we did, like that was like our initial attempt to figure out, okay, so if we have the target volume is, let's suppose, 0.15 in this case. So if we change the projected perimeter with a bunch of values, what are the different cost functions that we're going to get? And the conformal cost function is it's like a post-processing cost function. Like after we make sure that the designs that we got, they can be manufactured. And you can see, like as you increase the projected perimeter, so as you become more stricter in your projected perimeter approach, your cost function increases. That completely makes sense. But then this didn't really tell us. It told us, okay, for this particular problem, your optimum value lies between 0.2 and 0.3, but it didn't really tell us whether this target volume, scaling with target volume approach would be the best way to go. So then the other approach that we tested was scaling it with regards to the projected angle. And that gave us a lot more intuitive results with regards to what target OH value we should go for. So we tested that for two different problem setups. One is quarter pipe in the box, and the other one is a cuboid, which is subjected to the heat sink. So it's basically an extension of a 2D problem to a 3D. Yeah, it has just constant heat source generation. I'm talking about the top one, and the bottom one is, so it's like a quarter domain here that is modeled. So you have like a pipe that is a cooling pipe that is cooling the body around it, and you want to see how the topology optimization works in that case, and also like how this target OH scaling approaches work. So let's talk about the base case, no constraint topology optimization results. So this is for the first problem. So as you can see, the heat sink is on the bottom left of this problem. And you can see the features in red. So these are the features that your additive manufacturing approach won't be able to manufacture. These are the overhanging regions. Conductor volume here is 0.15 here. And you can see the temperature results are very intuitive. Like near the heat sink, the temperatures, you have lower values of temperatures, and the temperatures basically increase as you move away from its written source. It should be sink. So as you move away from the sink, the temperature is increased. However, the significant amount of constraint is observed. Notice that the projected perimeter here is 0.45. So we use this projected perimeter as a base value, and then we scale the target. That's the second approach that I'm talking about. And we scale the target overhang or the projected perimeter using this for the no constraint case. So that's, again, this is the no constraint topology optimization for the case 2, which is quarter pipe in the box. It's just a different physical problem, but we just so it's a different physical problem, but the methodology that we're trying it's exactly the same. So we're trying to know the base case projected perimeter, and then we're going to scale our constraint on the projected perimeter based on the base case. So yeah, so that's the question. What value of the projected perimeter should we apply to both cases so that we get a good trade-off between the designs that are manufacturable, but we also don't want to penalize too much on the cost function. So this was some of the implementation. So as you go from left to right, it's more of a stricter overhang projected overhang implementation, and the build direction is from top to bottom, as shown in the figure. And you can see that between 100% and 50% constraining the projected perimeter, the cost function doesn't really change that much. And you see this interesting behavior where the optimized topology finds itself basically rooting itself into the base plate. So you see that in the initial no projected perimeter design, you have like a lot of overhang areas. Whereas once you start implementing the overhang constraint, those areas are sort of eliminated, and the solver basically, it's very intuitive physically if you think about it, that it's rooting itself into the base plate so that those features can be manufactured. And of course, as you go stricter and stricter in the overhang implementation, you get like more stringent constraints on the overhang angles. However, the cost function jumps significantly, and at a certain point, so the optimum in our from the research that we did, this approach was much intuitive to figure out the optimum target overhang values. And what we found was between 25% to 5% of the projected perimeter is the optimum value for the target overhang. So this also checks out for our other problem as well, where we got similar results. Like there weren't too big differences between 50% and 100% in terms of the average temperature. However, like as you moved in a bit more stricter implementation, the overhang, your cost function shot significantly without really improving your overhang angle constraint implementation. So a good balance was found between 25 to 10%. And of course, like in these cases, you would need engineering judgment always, but it significantly reduces that uncertainty aspect. And colleagues over at NRC, they also did tests on the Thermo-Fluid aspects, and our approaches basically, they found similar ranges to work there as well. So that was like a good outcome of the project in a sense, basically. So just to conclude the presentation here, the heaviside projection method for the overhang angle control was implemented within the in-house diffuse topology optimization solver that was built at the NRC, and the implementation within the diffuse topology optimization, at the end of the day, what we got was manufacturable geometries to constraining projected perimeter, and it was also turned out to be an effective approach in controlling the overhang regions. The trade-off was found between the cost function and strictness of the overhang. Like I said, it's incorporating manufacturability constraints comes with a cost, and that's obvious. But the goal was to figure out a more robust engineering range where which engineers can use using their engineering judgment, and you basically use this platform to build in critical experimental setup design, assembling, and testing of such molds and dies. So with that, I conclude my presentation. Acknowledgements, of course, my postdoctoral supervisors, Charles and Bruno, who were very supportive throughout my postdoctoral tenure at Poly, and this work wouldn't have been possible without their guidance. And also special shout out to my colleagues at NRC, Marc-Etienne Lamarche-Gagnon in particular. He was a very close contact point who oversaw this project with a lot more rigor and detail. And we owe a lot of the success of this project to him and other colleagues at NRC as well, Marjan, Raymond, and Florent. And then the Metal Tech Consortium for providing us the platform to do this research, administrative staff at Poly and GERAD. And also for this, I was funded by Ivado postdoctoral fellowship, and also Fonds de Recherche de Québec, FRQ&T postdoctoral fellowship. So acknowledgements to them as well for the funding. And yes, that concludes my presentation.
Well, thank you very much, Saad. So are there any questions?